Hello. So thank you for coming to this session. I'm Jeremy Frey, the University of Southampton in the UK, and I'm responsible for this session, so we'll try and get underway. Just a few things for those of you here. Hopefully, that QR code will take you through to a Google Doc, which has in it actually some questions and thoughts about units and symbols from my colleagues here, but it's also a place, please, hopefully you'll get through to a Google Doc you can access. Otherwise, let me know and we'll try and fiddle with it, just so that you can put down notes. If you go also through on the website, you can get through to a document that has a summary of abstracts and titles for everybody here. Should have a link to that document as well, and also a link through to a meeting that we held in March this year at the Royal Society of Chemistry called Dust, which was essentially a similar sort of topics, and a link there to the talks and a summary document about that. We've got a number of speakers today. We're going to talk about units, symbols, terminology for data-driven science, from philosophy to pragmatism. So you see that I'm here. I'm going to be giving the talk for Vanessa. Vanessa is currently working between the University of Bristol and Athens and has a young child, so wasn't really in a position to either come or give the talk online. Max is here. Keris was also unable, for family reasons, unable to come to the meeting, and Elizabeth will be giving the talk for her. Blair is here, is fortunately giving his talk, as is Max, and Aileen is nearly 3, it should be about 3:30 in the morning by the time she gives her talk. She's in the UK, and Stuart is giving a talk on behalf of Stuart and Samantha, and he's in Florida, so it's only late evening, and he's probably watching the football at the moment, that American-style football. Okay, so you probably get used already to the sessions that run here. We will run with talks about 10 minutes or so, and there'll be a small gap between talks for questions, and then any time at the end we can continue the discussion. If you want to ask a question, can I ask you please to get up and come to the microphone? It's a pain, but that means that people online will be able to hear. And can you give your name and any other interesting bit of information about yourselves before asking your question? That will be great too. The organisers will be very happy. The session, everything is being routed through the Zoom, and I understand that is being recorded, and that we will be using that record to write up the meeting. And so we'll hope we are to distribute out to everybody a summary of the meeting later on. We'll again make that available on the websites. Okay, so let's get started. So I asked Vanessa to give a brief summary of the position of AI and scientific discovery. Vanessa is a philosopher of chemistry. Probably there's philosophy of science as an interesting discipline that has been running for really quite a long time. But philosophy of science, for most of my colleagues, stops with Thomas Kuhn and a few others in the 1960s at best. But there's been a lot of work done in there. A lot of it is philosophy of physics. In fact, there are many university courses that are philosophy and physics, philosophy of maths. We don't think there are any of philosophy and chemistry. So there are interesting gaps here in huge areas of chemistry, material science, engineering, where philosophy of science has not perhaps had as wide an impact as it might. And I think we're getting to the point now, particularly with AI, that it's very hard to overstate the importance that AI is making to contributions of science in chemistry, in the general physical sciences. The question is, to some extent though, what is the origin of that difference? What difference is it making to areas of scientific discovery? Technological impacts are high. If you want answers to things, you can get answers very quickly. And my example would be in the middle of the pandemic, you would like to know what is the next best drug to try to reduce inflammation response. You're not so concerned with why, but you want the next one. Afterwards, you want to know why, because you want to be better prepared the next time. So there are times when it's important to get an answer, and there are times when it's really important for advancing science, and indeed engineering, to get the answers to why. And that's much more complicated. So asking the philosophers who've been thinking for quite some time about what is the origin of discovery, what is the origin of the way science works, we have gone through a period of the socialization of science and the issues about correctness and the issue that we have the public when you actually go through and science changes its mind. But that's because evidence has changed. But that's really quite difficult to get over to people. So understanding that and the role that AI will have is very important. And that's why didn't I ask to illustrate this? It's because AI is fed with data. Data is the issue around codata and representation of that data and the units and so on, the symbols, has become even more important when it's a machine consuming your data rather than a person consuming your data. So all the questions that we've always had for hundreds of years, well, 100 and something years since Maxwell, of how to represent the quantities of the measured quantities we heard this morning, about measuring things and whether or not you can believe that measurement and validating that measurement. Well, if you don't know the units at the measurement, you've even got a problem before you've even started. And humans are quite good at working out what another human might have done. Computers are not very good at doing that. So AI has really made a difference. Now, yes, there's a hype, and I've recently got the university signed up to Gartner, and we've got the most recent hype curve. It's quite interesting to see what's at the top of the hype. And homomorphic encryption, a topic I was thinking of making some use of, because you can share your data without giving your data away, but you can do calculations on it, turns out to be at the very top of this hype curve. So maybe I'll just wait a little bit to see that. But discovery of new chemical substances, new materials, probably even more important than, more significant in AI, because the AI input is even more important there because of the complexity of the system. New ways of making things, new ways of taking things apart, which turns out to be quite important. Designing, I would put in myself there, designing for resiliency as opposed to optimal efficiency. We've generally designed to make something in the most efficient way possible, which turns out to work very well if you have a feedstock, which is perfect. The modern world, you do not have feedstocks, or you may not want to have feedstocks that are perfect. How do you design something that still is pretty good, but doesn't matter if you turn the tap one way or the other? Bringing in the complexity of quantum calculations, which are getting more and more powerful, and maybe we'll even have some quantum computers, bringing those in together with the data. This is an area where AI is certainly, in chemistry, making particular contributions. But is it making an impact on the science itself? And certainly we do things differently, but this is where the philosophical question comes in. Because what we're talking about there is how are we improving our understanding of chemistry or physics or material. Actually, as a long time ago, 45 years ago, when I was sitting in a room with Malcolm Green, a very then eminent inorganic chemist, and he said, if I went up onto the mountain and I didn't come back with tablets of stone, but I came back with a book that listed all the molecular orbital energies of any compound I ever might want, would that be of any use to me? To which his answer was no. I still wouldn't understand anything. I wouldn't know what was best to make, why to make it, how to make it. I'd have a useful bit of information, but wouldn't really be the answer to the understanding of chemistry. So how do we understand our progress? And this is why philosophers now think at this point.
What constitutes
Vanessa will
scientific progress? There are many different features that have been associated with the idea of progress in science. One thing is we have progress when we manage to make successful novel predictions. So, for example, Mendeleev's classification of the periodic elements was considered a big sign of progress in chemistry because with the gaps within the periodic table, chemists managed to predict new elements and later on discover them. This also brings us to the second feature of scientific progress, which has to do with discoveries. So discovering stuff or new material that are of use in some way is also a sign of progress. Of course, explanation and understanding, providing explanations of why a certain phenomenon occurs and understanding better the mechanisms underlying, for example, a chemical reaction are also features of scientific progress. Achieving numerical accuracy, developing models which can predict with better accuracy the value of a certain measurements, for example, or approximate better certain observations is also a sign of progress. Of course, technological applications that have a societal impact is also something very important and constitutes progress achieved through science. And lastly, truth and unity. Science is said to be important and to to be positive towards humanity because it achieves truth. We manage to uncover what are the true mechanisms that underlie the phenomena we observe. But also unity. This is another important value that is often associated with scientific progress. So it is often said that science progresses because it has managed to create a theory that unifies our understanding and description of a variety of seemingly diverse phenomena. So how does AI fare with respect to some of these features that characterize scientific progress? Well, it seems uncontroversial to claim that AI contributes to progress in the sense that it has accommodated scientific discoveries. Scientists have discovered new substances that are used to synthesize new drugs. They have discovered new reaction mechanisms, and that is through the use of AI. In fact, AI's ability to accommodate discoveries is based on the fact that AI makes successful novel predictions. So here, the idea of progress, which is accommodated and satisfied by AI, is the idea which is connected to the achievement of novel predictions. But what about understanding? Does AI accommodate or enhance the understanding we have of the world through science? Well, here problems start to emerge. And one of the main and most persisting problems that scientists have with AI is the so-called problem of opacity, which very crudely is basically the problem that we don't know how AI produces all these successful prediction it does. There are two main types of opacity that have been identified. So there is the so-called access opacity. There is opacity with respect to the learning sample of the training engine, of the learned model. So we don't really know how the learning sample is used in order to produce successful results through the model. There's also link opacity. This occurs when a system, according to Facchini and Termine, it occurs when a system that is used to model a given target phenomenon conveys inadequate or insufficient information about the elements that are relevant for explaining, predicting, and controlling such a target phenomenon. Now, opacity, the problem of opacity, is quite a problem in the sense that without knowing how and for what reasons AI produces the result it does, we cannot really say that it can contribute to our better understanding of the phenomena, because in a sense it just spits out results that we can then use in order to discover and predict new stuff. But it doesn't really help us understand the underlying mechanism that explains the specific results it has given us. And this also is connected to explanation. So explanation is another feature that is associated with scientific progress. And here we have the second problem, which has to do with the problem of models, right? So AI models certain phenomena, but models are strictly speaking false. So they produce results that are or are based on physical impossibilities. Also, this problem is further enhanced by the fact that the learning sample which is used to train the AI models are not drawn from an underlying theory, and this is problematic because it is often the case that they might produce results that are physically impossible. And it is very important to be able to recognize and identify those physical impossibilities that are produced by the AI models. So we are in a situation where AI models have a very strong predictive power, but they lose with respect to explanatory power because by themselves they are unable to detect potential artifacts in their results. So this undermines the ability to explain through AI. A solution that has been proposed by computer scientists is the development of what they call explainable AI. So here they are trying to develop models which in turn will try and explain the way in which AI produces the results it does. But this seems not to be a very complete solution to all the problems mentioned above, because explanation here, as Rudin says, refers to an understanding of how a model works, but not an explanation of how the world works, right? And this, as Boge also has pointed out very recently, may lead us at a result where AI may allow us to make new discoveries, but scientists will have a hard time understanding them. So it is not entirely clear yet whether explainable AI will in fact resolve these problems which hinder, explanation and understanding through the use of AI.
So the solution that Vanessa suggests with this clarity the philosopher brings is that we can use AI as an instrument, a colleague. It's not an answer. You don't expect it to have truth. And if you actually view it as just a further part of your experiment using the AI systems, then we might have a way through to using it reliably. And it's not a particularly revolutionary view of AI, but it is actually somewhat different from some of the views that you get from those technical companies, the big techs, going towards general AI. So but the other thing that I would like to view is that we are thinking about bringing in this philosophical view gives an underlying connectivity, a way of looking at things to understand what are we trying to do when we're trying to explain what our data is. And our part here is to communicate that data with the units, the symbols and so on correctly. But since we're trying to get it to lots of different people in lots of different ways, to do lots of different things with it, there may not be a single solution. What we do need is some underpinning to start an approach so that we can actually work out where we go with all the sort of techniques that we're trying to deliver. And that will then mean that if we feed that sort of consistency in our scientific practice to the modeling, to the areas, that we'll actually be in a better position to actually build reliable models built on reliable data. But what we're talking about here in this session is how to communicate that reliable data with all the relevant metadata that goes around it in a usable manner. And that's a theme that we'll be running through. There are the right thing to do, and there's the thing we can do, and there are things that we can persuade people to do, all of which have big question marks over them, and we're trying to bring that together. In her absence, I'd like to thank Vanessa for putting those slides together. If there are a few questions, now I can open up just a very few questions, but I'll try and answer them. But if we record any questions, we can get Vanessa to provide answers. So, okay, thank you. Are there any questions? Sorry to make you come out of the microphone. We'll only have a short period now because it's gone a bit longer.
Yeah, so,
I think so.
Okay. Okay.
Yeah. So you give your name and.
Stephen DaCosta from Link Digital. Yeah. So my question was, there was no mention of sort of like constructor theory in terms of the philosophy, and no mention of like Karl Popper in terms of evolutionary knowledge. It seems that I would just sort of like to refute the idea that AI is an instrument. It's much more of a substrate, or it's much more of a construct within which it has its own dynamics. Mm-hmm. And if we don't address that and the variance within that, then you can't simply call it an instrument. And I think the specifics there would matter almost all the time.
I think you're absolutely right, and Vanessa will be in a better position to answer this. Yes, I think these things start with Popper and verifiability and move on. And I think the point about calling it an instrument is not that it's an instrument in the sense of being a completely passive instrument that you might just switch on. It's that it's not an oracle. That's, I think, the important point, that it's something to engage with. And yes, it has things built into it, and there are things that we have to ask about it and understand about it. And I think you're right that the last 60 years worth of history of philosophy of science has a lot to provide us with, about a basis on which to start saying, I've got this new thing here. How new is it? How different is it from people, instruments, experiments, and really that's what I wanted to set the scene here, that people are aware there are questions to be asked, and there are a group of people who have been thinking about this for quite some time, and that it is worth our while to study what those people have been up to. And you've plotted one direction through. Bruno Latour has another sort of direction through things, and actually spent some time observing biochemists in labs and thinking about what they wrote down and how they came to conclusions. So there's a wealth of work there which is generally missed by those of us practicing in the lab. And I think it really, there's a lot of things that we ought to be reading about. And I know Vanessa tries to publish articles in Chemistry World, but others, to try and make that accessible to the scientists who are not being schooled in that. In the UK, at least, this sort of philosophy of science is not taught to undergraduates. In France, I think we find a lot more is taught there. And I think that's something. Okay, time's up. If we do need to move on, please, if that document did open, did anyone manage to open the Google Doc? Okay, put questions in there and we'll get back to you. Comments, things we should do, they will all contribute to the summary. So if I can introduce Max, go and give the next talk. Max is originally a computer scientist, part of the Go Data Drum task group, but importantly works with the BIPM, and others, and he will talk about the SI reference point.
So the whole session is about also about unit representation. So I want to talk about one specific, or should I? Yeah, one specific unit representation that is currently, in the making, so to speak. It's more or less the language model for the SI brochure. But to give you some more context about it, because I don't think that everyone here is working for a metrology institute. In 1875, there was a quite big achievement, and that's the Meter Convention. So that's an international treaty. It's has big international support, and this is the community that provides the international system of units. So, this is updated regularly. We don't have the same version as 1875. We got a few new units since then, and also some redefinitions. But this is like the community I'm speaking from here a bit. And this community, at least at the highest level, they communicate in resolutions, and at the last big meeting, or so the General Congress of Weights and Measures in 2022, they also had a resolution on the global digital transformation of and the SI. And in that resolution, it says they want to prepare the Meter Convention to extend its role also in the digital era, to be still the accepted anchor of trust regarding to units. And they wanted to have something that is globally accepted, but also is compatible with other existing digital standards, but also will be backwards compatible to these more non-digital solutions that have been. The SI is basically a big interoperability, analog interoperability project. So, and the last thing is also that, or not the last thing, but that this digital representation of the SI should be following the FAIR principles. So that's a bit the context for the development I want to present. And based on this resolution, there was the decision that it should be started to develop something like that, which is digital, which is fair, which is machine actionable, but also follows current standards like semantic web standards, tech stack, and linked data concepts. So how do you approach something like that? So first of all, we have seen that cartoon maybe in one other session yesterday. We might have a situation like that currently here, or you feel like this could be a situation like that. However, this was not the intention behind it. We don't want to build a 14th or 50th unit standard here that is better than everything else, but it should the intention is rather to provide an authoritative reference to units and that complement existing unit standards with the information that is already available in the SI brochure. And in doing so, we followed classic ontology engineering practices. So identify main concepts, ask or propose competency questions that you want to answer with your knowledge model, decide on what kind of reasoning capabilities do you want, do you need, do you want to provide to the user, what kind of technologically details do you want to use, which kind of technology you want, and also how should users be able to interface with that knowledge model. And if I say we, I mean a rather small developer team. So that's Stuart, Gregor Doodle, Jean-Laurent Hippolyte, Frédéric Ménadier, and Janet Miles. So Frédéric is working at the BIPM, so the International Office of Weights and Measure, located close to Paris, but not in Paris. And yeah, just to give you an overview, what's the current state of that? What are the, I said that identifying the main concepts and relation is more or less the first step to do. And in the SI reference point, or the SI brochure, it's a lot about measurement units. So the central concept here is a measurement unit. And then for the brochure, we have multiple important subclasses of that. So we have a base unit. So these are the 7 defining units that make up the SR system, more or less. And for these 7 base units, we also have links to their definition, to historical definitions, as well as the current definition. We link those to the resolutions from the specific General Congress of Weights and Measure. And every base unit also has a constant, which is linked to the definition, because sometimes these change over time. So the constant is not linked to the base unit, but to the definition of the base unit. And then there are also other more explanatory attributes that I just highlighted with 3 dots. And then we have the power of the SI system. So we can construct units by combining existing units. And these are like prefix units. We can have a Newton meter, which is a compound unit in that sense. So we multiply 1 or 2 existing units with each other. We can also have like square meter, which is a power of a unit, or per second. And this also is reflected here. So we can construct arbitrary units as it is on paper. We can also provide an ontological representation of that, or semantic representation. But to make this a bit clearer, I want to give one example that I think showcases almost all the aspects I just showed. So if we look at the Newton, 1 Newton is meter kilogram per square second. So we can provide a turtle code for that. And I mean, turtle, I think many of you have seen turtle before. It's a way to capture a knowledge graph. So the implied graph here would be, we have the unit Newton, and we know it's a special named unit in the SI brochure, so we know it's a measurement unit. We have the link to the specific resolution where it was defined. We have a symbol for mostly backwards compatibility. We also can link it to certain quantities that are measured in that unit. And then we can provide the same, or the Newton, in a base SI representation. And this is where these compound unit or these more or less mathematical expression of a unit come into play. So we say, okay, we have a unit, the Newton is in base units a unit product of 2 other things. And then because we have left and right terms, we can also have another product, and then we have a product with a unit power. So you see how that trickles down and captures the full knowledge here. So you might ask, okay, how can I access that? We have multiple ways to access the current state of this SR reference point. We have a cool looking QR code that brings you to an overview page. There you have the possibility to just get some basic information. You also can download the turtle files that make it up. And you have the possibility to open a query tab. And this is just a Sparkle endpoint where you can query the knowledge graph of this development. You also have the possibility, you have the possibility to do REST API calls to the same address. You just need to use different HTTP attribute headers. And then we have the GitHub side of things where you can actually see the developed turtle files. But please keep in mind, as of now, officially, this thing is still in beta release. We are still requesting, or we are grateful for any feedback. And that's also how the GitHub can be used. So you can open issues on the GitHub. If you find something, we try to fix it. Although some things are not really in our hands. So sometimes certain decisions might have two solutions from a technical perspective, but the implications of that solution are not our decision. So far so good. Of course, we had this cartoon in the beginning. How does this relate to other, or could this be just another unit representation framework? And in order, yes, all right. In order to not do this, but just be the authoritative reference to the meter, to the second, to the Newton, we try to incorporate the SR reference point or links to the SR reference point in other knowledge representation frameworks. And for example, the QUDT ontology, which is, I think, quite popular for unit representation, already has a QDT SI exact match attribute. And if a unit has an exact match, I think Stuart did a lot of work to link the specific SI reference point equivalent. Also, a work from Stuart that we might have further information later during his talk is a service that provides the same unit in different unit representation frameworks, and there the SI reference point is also a part of. There are also conversion packages for, I'm not sure how many of you are in the subject or related to or have contact with calibration certificates. In the digital calibration certificate, there is a specific or a special notation of the units, which is called DSI. And there is a Python package that mainly I authored that can provide the conversion between these turtle expressions and the DCC-related unit representation. And there are also currently ongoing discussions and preparations to include a reference to the SI reference point in the IEC Common Data Dictionary on units to have that link as well. So in general, in 2022, the CGPM decided to, or encouraged to develop a globally accepted digital representation of DSI. And with this presentation, I wanted to show you what's the current state of the development of that, what are the fundamental ideas and concepts that we identified, and what could be next steps. So with that, these are the, I think, important links I mentioned throughout the presentation. So if you are not familiar with the metrological community, the BIPM, or so to speak, the office of the meter convention, has certain members, and these are listed in the first link. And then we have the we have the link for the QR code that you have seen. We have the link to the GitHub where you can provide issues or feedback of any sort. And we have the resolution DOI. So with that, if there are any questions, I'm looking forward to that. Otherwise, we can also discuss that after or in the lunch break.
We're running a bit behind time. Any quick questions? I'll certainly put questions into the document and find that later. Okay. Thank you very much. Let's just take thanks again. And now we have Elizabeth and Keris. And we should be there. So Elizabeth and Keris both work a number of different things, but importantly in the Physical Sciences Data Infrastructure Project. Keris has spent many years working at IBM in usability, and that's a theme that actually is both key importance to both Keris and Elizabeth. Over to you.
Thank you. As I said, right. A bit short. So, right, let's get on. So quantities, not quantities, and making sure our data is useful. As I said, this is a presentation that Keris has put together and unfortunately couldn't make it to come to Brisbane today. But she has done a little... Yeah, I need to click on something in a minute. But she has recorded a little message for us all. No, where is it? Oh, no. Sorry. No, sorry.
Hello, I'm Dr. Keris Willoughby from the University of Southampton. I'm very sorry that I'm not able to be there at IDW with you. I'd like to thank Elizabeth for giving my presentation to you in person. As part of my role on the Physical Sciences Data Infrastructure Project, I'm interested in looking at how we make scientists better at sharing their data and how we make software easier to use. This presentation is going to give a brief look at how different scientists do their research, what quantities are important for different disciplines, and how things other than numbers are important to make the numbers meaningful.
Right. So just to stress that any deficits in this presentation are down to me and my presenting, not Keris and her slides and her great presentation that she's put together. I just want to make that very clear to start with. So as we start, quantities are a little bit confusing and trusty dictionary definitions are a little bit contradictory. You might already have seen some of these definitions before, so you'll know what we're talking about. But we need to think about them because we do a lot of measuring in science. It's a little bit of an understatement, possibly. Counting is an innate ability of many animals and not just humans. So this side of things is relatively straightforward. We have some objects or abstract concepts we can count, such as 8 mammals, and here, and the 8 sides of this octagon. In science, at least, spatial measurements, like distances, probably do count as quantities. The distance is a number of meters from the start and the finish line of the race. And in science, a quantity can also be a symbol that represents a number. For example, pi represents a dimensionless quantity, a constant number without units. But quantities can get complex, and I'm sure you hear more about these, or will be, and have. But for example, there are many dimensionless quantities, such as ratios and ranges. So a lot of the data we share are quantities. This might be a PDF in supplementary information or as separate data files such as CSVs or Excel. And a lot of what we share are quantities, as I just said. It's often the case that these data are presented with limited information to indicate what they are. If the data is separated from the paper, it's often meaningless. So the data here on this slide has lots of numbers, but no meaning. Some are quantities, some are labels, but can you tell? So we can make the numbers more useful by adding additional context in the form of metadata. A title provides an explanation of what the data is. The labels become more meaningful. We begin to get information about our units, what we are measuring, So here we've got the number of periwinkles of different colours and that we are doing that in different locations. Even so, even with this metadata, we can still do better. We want rich metadata. We can be more specific. So which species are we looking at? Where exactly? What is our sample area? What are the colours? And it matters that we are looking at periwinkles on different types of rock. So this is much improved, but we can still do better. So we need to be able to link the data collected and shared to more information. Exactly how did we collect the data? Our processes, methods, techniques, and equipment. Exactly what are we researching? Using species taxonomy, we can link to other data about periwinkles, genetic data, ecological relationships and roles, habitat preferences and geographical distributions, life cycle and behaviour habitats, physiological data, and so on. So what else matters? The weather, the season, tides, wave conditions, and other environmental factors could all impact our counts. So what did we conclude from the data? What does that fit in with other studies, and how using identifiers helps to link the data to the provenance and additional context required to make sense of it all. So, quantitatives and their metadata also underpin the other kinds of output we share, graphs and narratives, etc. So we measure different quantities, we create different records and generate different outputs to communicate our different disciplines. And there's just a few more examples that we'll go through now. Excuse me. Archaeology is focused on producing a narrative, often of a particular place at a point in time or changes over time. In the field, there are a lot of spatial measurements to determine where features are in the landscape or where artefacts were found, represented as maps or surveys. So materials such as soils, organic material and artefacts can be examined in the lab to determine composition, dates, size, abundance. Qualities of structures and artefacts can be determined as well as measurements, such as the identifying artefact's purpose or association with cultures. So metadata connects the data together. Everything has identifiers that enable a link between central excavation logs, individual field diaries, artefacts, samples, photos, maps, drawings, and the lab-based data. Geology has some similarities to archaeology. Measurements in the field are often spatial, with data encoded into maps and logs that show the geological layers and structures in 3 dimensions. Measurements in the lab are used to determine the makeup and properties of rocks, minerals, and fossils. And whilst other aspects are more qualitative, such as shape, textures, colours, and lustre, some are rather subjective. You can catch geologists gnawing on rocks to determine their grain size. Metadata connecting things together is a little less organised than the archaeologists, but the information in the notebook with photos, maps, sketches and samples use identifiers to help locate the elements at a specific locality. So now, data collection in chemistry. Chemistry is primarily a lab-based discipline, although the measurements being taken can vary quite a lot depending on the science. Hopefully you will hear more about the specifics of quantities in chemistry at some point in this talk. Some measurements are done at the lab bench and are typically recorded in a notebook, still often paper, but increasingly digital notebooks, which can help with capturing the units and metadata in a consistent and structured way. Other measurements require larger and more complex instruments. In some cases, samples are sent to specialist centres for processing. The instruments produced data files that can capture, or not, the metadata in a helpful way. And crystallography is a really good example of well-structured and consistent metadata in chemistry, with data created in a standard data format with expert curators that prepare the data for sharing. Data is typically linked together through experiments, samples, and chemical identifiers. And outputs of chemistry are typically numeric, creating tables of data or properties of materials as shown here. But how do we ensure that we capture important metadata to go with the measurements we make? We need to capture the metadata and the context at the point we generate the numbers. At Southampton, they call this the curation at source. It's much easier to create the metadata at this point than it is to try and add it later. Standards are vital, and embedding these in our scientific tools makes the process easier and enables the metadata to be used within the tools in an intelligent way. Our tools should be automating as much as possible. If it's possible to identify the right unit, do so. If not, prompt the user with suggestions. Even without standards, templates can be used with placeholders for metadata to prompt users to add the metadata in a consistent way. And metadata literacy can help to explain what metadata is, why it is important, and how to do it for a particular discipline. Instruments and software should be adding the right metadata automatically, ideally with standards, and including other useful contexts such as specific Unix, calibration parameters, versions, and transformations, and so forth. So, in summary, sharing data without the context makes the data useless. Sharing the data so it can be understood and reused is important, and I would actually say is vital. Standards are important here to connecting, meaning, and making the data machine actionable. And don't underestimate how sensible file names, folder structures, and readmes can be for giving some extra context. So, thank you for listening. Karis has written here, thanks again to Elizabeth. I'll take that praise. But thank you very much for Karis, really, for this putting together this talk. And you can find out more about the physical sciences data infrastructure and our work at psdi.ac.uk.
Again, I think maybe just put questions for Karis in the notes, and we'll get them answered asynchronously. So thank you for that. And I think that to set the scene there, the metadata is really important. We want to share things. And Blair, who works for the National Standards Institute in New Zealand, will be talking about the interoperability here, which when we're sharing data, we've got, and we're providing maybe the metadata, if it's not interoperable, we don't win. So hopefully, it should just...
yeah, if you just help me with this.
Just go...
I'm hopeless with computers.
That was just the... I'll stop that in a moment. What can I do? Why is this not going on to... There we go. That there. Great.
Thank you very much, Jeremy. Thank you for coming to listen to the session, to all of you. So, as Jeremy said, I work in the National Standards Laboratory of New Zealand. I'm a metrologist, not a meteorologist. There's been a bit of confusion over that. And so I'm going to talk to you a little bit about interoperability in the general context of units. But I'm going to try and give you, in a very short space of time, an idea of an enhancement, if you like, to units that we're calling the M layer. So I'm just going to try and seed some ideas about that with you, because Aileen's talk is also going to consider the M layer a little bit. So first and most importantly, perhaps, what are units for? What are units for? Our unit system, the SI, was developed was an idea from James Clerk Maxwell in the middle of the 19th century. And this is what he said they were for: to transform our results from one system to another. So he was already thinking about interoperability. He was thinking about how, if I'm given some data in one set of units, can I get it to another set of units? And that's that, to me, is the essential problem that we have. We've got a transactional situation. We've got people who produce data, and those people don't necessarily know what the consumers of that data need in terms of the format of their information. So the producer will put some units on a report, but the consumer may need a different set of units. And so that it falls on them the burden of converting from one format to another. And we repeat this over and over and over again, right? So what Maxwell did was provide a methodical and systematic way of doing this, which greatly improved the situation. But it's time to do a little bit better. So I'm going to go quickly through three sort of scenarios, called them use cases, just to try and motivate the ideas behind this M layer. So we have, first scenario is we're sending a spacecraft to Mars. It has a method of propulsion on the spacecraft to try and trim its trajectory on the way. Somebody has built the propulsion system. There's a parameter, a physical parameter, the thrust that will be produced by this engine. So this has to be conveyed to the people who are driving the spacecraft. So How do we do this? Well, what are the strategies for interoperability? We could just simply say you must report your units as newtons, thrust as a force. That's tried and true and usually works, but there's a famous case where it didn't. We could say, software can help us. We can have a unit-aware software system on the consumer side, and it will detect if something's not quite right. Or we could say, could we not have a unit-independent software that can accept and consume things in different formats? So let's leave option one behind, because that's really 20th century solution. Unit-aware software, what would that look like? Well, if we're expecting something in newtons, there are effectively equivalent ways of giving that data. And Max mentioned that a newton can be thought of as a kilogram meter per second squared. If you start thinking about prefixed versions of those of units, if you start thinking about special named units, you really have a lot of choice here. And it could all be giving you the data in newtons. So that's going to put a burden on your consumer software. It would have to recognize these things in order to be effective. So we haven't really got out of this bind all the responsibilities placed on the consumer. Option three, unit-independent software. We often think that this should be easy because we write equations in terms of quantities and we don't put the units anywhere in them. Here I've written an equation for the power of the engine as being the thrust times the velocity. No units anywhere, that's a physical equation. So if we're going to do that, what would our software system look like? Well, first of all, you can go through and say, what are the equivalent units to newtons? What are the equivalent units for force? And you can map those out, you can itemize them, and you can think of that as a sort of a graph, that if you're sitting on a node in that graph, then that's a particular unit for force, and the edge to another node is a transformation that you would need to go from one to the other. So that's the idea shown here in that figure. This information can be collected and centralized and then used by many people. So you don't need to do this yourself. It could be a service that is built and made available. And in this way, the consumer and the producer will be on a more equal sort of ground. Now, it's not enough just to have the units. So here's an interesting use case. I was talking to somebody about this just yesterday. The optical spectroscopy, they often report the energy of photons. They're firing photons at materials and looking at the response of the material, but they often use different units. And they can say, look, our energy's in terahertz, that's a frequency, it's not energy. Reciprocal length. So you're looking at just the units and the number, you don't know what you're looking at. What we need is the nature of the quantity that has been measured as well. And so this is something extra that is going to have to be included in the system. And I'm going to call that the aspect rather than the quantity. We saw a lot of quantity in the previous talk, but the word quantity is used in many different ways, and it's not always the way in which the system would have to interpret it. So it's much better to set aside a term aspect and say you need the aspect, and that's related to quantity, but not necessarily directly transferable. Now, physical quantities. I'm a physicist, and physicists are a bit elitist sometimes. Physical quantities are a class of abstract entities. We can write physical quantity equations, we can have models and things, but a lot of data isn't really compatible with the idea of a quantity. We have materials properties. We've had some interesting discussions about that. These may be reported in SI units, but the quantity themselves is not really qualified as being a quantity. If you've measured some of these material properties, you need to know how you've measured them against certain standard methods. Otherwise, the results are not necessarily comparable. And I think this happens a lot in chemistry too. So we need, we have these various quantities. We also have things that are clearly not quantities. For example, coefficient of intelligence coefficient, IQ, gross domestic product, the Beaufort wind scales. There are lots of things that are not quantities. So in the middle of the 20th century, there was a bit of a furore about this. And Stanley Stevens at Harvard pointed out that there are really a variety of ways in which measurement is applied, and we can classify those ways. We can classify according to the mathematical structure that produces, and these are scales of measurement. So we need to think about the scale of the measurement and the form of the scale. And what's an example? Temperature. The units of temperature are really not enough for you to use temperature data. If I tell you I've got 12 degrees Celsius and ask you to convert it to Kelvin, there are two responses possible. It could be 12 degrees Kelvin, 12 Kelvin, or it could be 285 Kelvin. That's because there are the different scales occur in different situations. A temperature is an interval scale which is offset from absolute zero. A temperature difference is a ratio scale. So why is that important? Well, here's Antonio Guterres, the Secretary General of the United Nations, commenting about how hot it was a year ago. Temperatures topping 50 degrees Celsius around the world, that's halfway to boiling. But it's not, is it? It's a lot closer than halfway. It's halfway from freezing to boiling. So it's a very nice argument that he's making, but it's not technically correct. And so what this M layer is going to do, or does, it's going to capture the type of scale on which data is being expressed. And there are only a few types, there's half a dozen or so. So if you're going to build something, you really should know why you want to build it, what that's for, what you're going to build, and how it's going to work. So it's nice to have a high-level picture of what you're trying to do. So here, the M layer, we want to enable transformation between valid alternative forms of expression. That's more or less what Maxwell had in mind. We want to, we want to enable interoperability. We need to represent the formats unambiguously and their relationships. We need to capture that, and that's what I showed you in the earlier slide. So we need to form these graphs and the linkages between them. And then how are we going to do that? Well, you define unique identifiers for the expression formats and the legitimate format transformation. So how can you go from one node to another? Can you go? These are open questions. So distinguishing between transformations that preserve invariant properties of data, stay in the same class of scale, and those that don't necessarily preserve it. So you might go from an interval scale to a ratio scale. Or sorry, vice versa. So that's what we're trying to do. And what this will do, it'll balance the playing field so that if a producer and a consumer agree to use the M-layer identifiers, then the consumer, if they want the data in a different format, they have the identifiers for that format, they have the identifiers for the way it's been provided, and the M-layer will tell you how you get from one node to the other. So the M-layer will have a triplet of pieces of data instead of a pair. The traditional expression is value and unit. The M-layer will have value, aspect, and scale. So for example, in the M-layer, if you want to say the mass of something is 70 kgs, it's more like saying 70 is the mass expressed on a ratio scale in kilograms. It embodies that amount of information. So in terms of your data, you'd have two identifiers, one for the aspect and one for the scale, instead of one for the unit. How does the transformation work? Well, if you have the identifiers for your data and you have the identifiers for the format that you would like, then you can query the M-layer and it will respond. If there is a translation path, it'll say this is the formula. If there's nothing there, it'll say, sorry, that's not a legitimate transformation. So, to summarise, the Maxwellian system, the SI system that we're all familiar with, these are designed for skilled people. Maxwell was working in the middle of the 19th century. He expected scientists to use what he was describing, not computers, which are considerably less adept at using tacit knowledge. So to support more forms of scientific data with less reliance on human intervention, we need to generalize the formats that we have at the moment. The MLA is based on fundamental metrological principles, and that means it can unambiguously support many forms of expression for measurable properties. This goes way beyond just your elite physical quantities. So we are building this. It's being done within a group called the National Conference of Standards Laboratories, which is in the United States. There is an API that you could go and have a look at, but please remember this is under construction, so it's a bit of a construction site. It doesn't have the nice veneer that we would hope it would have at the end of the work. So thank you very much. It was a quick tour, but hopefully I managed to explain things.
Can we switch to online and got Aileen, who's way at home, who is a researcher in with the civil sciences data infrastructure project, previously worked for the Royal Society of Chemistry, and not quite sure whether I need to bring up slides like that, where she's going to take over online. We need to get rid of I need to go on. Get Aileen coming up here. Are we okay to go online? Yeah, Hi Aileen, are you okay?
Hello, can you hear me?
Yes. Yeah, that's
great.
Go ahead.
Okay, and you can see my screen?
Yes.
Great. Hello everyone, it's nice to be dialing in. I hope the weather where you are is a bit nicer than where it is where I am. It's very dark, it's 2:30 in the morning here. But I'm very glad that I can join in whatever way that I can. I work for PSDI, the Physical Sciences Data Infrastructure. I think Elizabeth mentioned it in her presentation. So I'm going to do a really quick what is PSDI explanation. I'm going to talk a bit about the metadata in PSDI, which I'm responsible for. I'll outline our requirements for units in PSDI, which we're starting to think about now. And following on from Blair's presentation, I'm going to tell you a bit about my thought experiment in how we might be able to use something like MLayer to handle units in PSDI. So firstly, what is PSDI? PSDI is a data infrastructure for physical sciences UK research data. And it's been funded by the Engineering and Physical Sciences Research Council, the EPSRC. The lead institutions are the University of Southampton, where I'm based, and the Science and Technologies Facilities Council, STFC. There is a first version of PSDI now available at the website shown. So if you want to have a look around it, then feel free to do that. I'm not going to talk much more about PSDI because you'll get a better idea of what it's about as I go through. And in particular, as I talk about the metadata, which is my field of interest. So we're taking a top-down approach for the metadata in PSDI. We're starting at the top level and we're working down. So so far, we've mostly been focusing on metadata that describes the resources that make it up. And we're starting to think about how to define the properties and the units within those. We've not really got to thinking about metadata on the data level within those resources or the data provenance. As you go down, there's a lot more of this data, and it gets a bit more complicated. So we thought we'd start at the top and work down. So we're somewhere around here at the moment. We're trying to use existing standards where possible. So CDIF, which I'm sure you all know about, and there are many different sessions about that during this week. That's been something of a major guidance point for us. We took its recommendation to define a top-level SCOS vocabulary to define the PSDI terms, and to use DCAT for the resource catalogue. So CDIF recommends either DCAT or schema.org. We went with DCAT. So those are kind of following directly from the recommendations of CDIF. For the data description, we've kind of gone slightly off tack from CDIF, and we're using Optimade as the basis for our PSDI cross data search, which I'll tell you a bit more about. So this is kind of slightly off piece, but we might revisit this over time. There might be different ways that you can access the data in PSDI, one of which is these. And then I think it's fairly standard that if there's people, we use ORCIDs. If there's organisations, we use RAW. So where possible, we try and use standard ways of doing things. And we're trying to follow that for units as well. So our first point of reference, CDIF, what that says about units of measure, it comes under a category of profile that CDIF calls universals. This is a screenshot of the CDIF handbook. But the main points of this is that it says that we should use a common coding system, and you can effectively tag up if you have any quantities or properties with one of these kind of standard coding systems. So this sounds like a sensible way to go about things. And these suggestions were useful. We've not got so far as to look at these yet, but they are on our list to look at. But this was kind of a starting point for how we were starting to think about units of measurement. So in PSDI, we've got a general kind of structure where we have some services and tools that are owned by PSDI that span across the whole platform, and it's arranged in different resource themes, which are about a specific scientific theme, and it groups together data, services, tools and guidance by different research groups, different PSDI partners, which all kind of link together in the PSDI platform. So one of these services is the cross data search, and this enables search across all the compatible data sources in PSDI. So this is a very powerful tool. That it's not, PSDI isn't just a way for you to go to each resource theme and explore that separately, but it allows you to search across all of the data sources that are compatible, depending on the property that you're looking at. So not all properties in all of the data sources are searchable across the cross-data search. It's only those which match standard property definitions. So the resource themes can have whatever properties are of relevance to them, but if they match these standard property definitions, then you can plug them into the cross-data search and make them findable via this. So currently there's very few properties with units in the cross-data search, but this will grow in the future. So this is something that we're starting to think about now. The example that I show here is unit cell lengths, which are searchable. The values given are in angstroms, and the values that they're stored in the data sources are in angstroms. So there's no unit conversion currently. So this is all something that we need to develop. The cross-data search uses Optimade in background, I mentioned. This relies on the properties that you're searching on, matching definitions in the structures endpoint we used initially. There's the references endpoint, which brings back a reference to a publication. The structures endpoint is kind of the 3D structure, and there's development going into a cheminformatics namespace and a SIFT namespace, which are about properties that are relevant particularly to those areas. And we're helping to agree on what those property definitions should be as we're using them in our cross-data search. And there will be more properties that we can define in the way that Optimade is structured. You can have a PSDI namespace. So this is how the properties are kind of standardized. I should say I'm using the word properties here. Some people might call those variables or fields in the data set. So in Optimade, you define the properties. This is a snapshot of the GitHub where that cell length is defined, the cell length that was in the cross-data search, and it has the definition here. There's also a human readable version of this, and it has a link to the unit. The units are also defined in Optimade, again in the GitHub. They can be very specific. So for example, for the meter, you can go to the year that the meter was defined in, or you can link to a more general form of it. And it links out to other resources that define the unit as well. So we talked about mapping between the unit systems, and this is available in the Optimade unit system. So one thing to highlight is there's no unit conversion in Optimade. There's a fixed base unit that's defined for each property, and every data source has to work out for itself how to serve up the values in that property. So in PSDI, we would like that to be a bit more flexible. So if I think about, for example, if we were going to add melting point to the cross-data search, which is something that we would like to do that's not already in there, we have some PSDI data resources which have that property in them. And what we would like is that the user who's doing the search in PSDI could put in their search criteria in a variety of units, not just one, and that it would be able to search different data sources where the melting point might be stored in different base units, and it might even have a data source where where different values of that property are stored in different units. So we want to allow unit conversions on all of these different levels and unit definitions on all these different levels. So I've made a list of the unit requirements in PSDI. Because of the time, I'm not going to go through all of these because I actually go through these particularly with reference to how MLayer meets them. So I will cover these, but not in the slide. The idea is to investigate those unit requirements with these different ways of dealing with them. We haven't done most of this work yet, but we have looked at MLayer because Blair was visiting us, so it was a good chance to sit down with him and work out how that would work. So moving on to MLayer. So the first requirement was, does MLayer link to a definition of a unit? So here we've got an example where I've looked at the MLayer API to see for the example of the unit cell length, just to see how would we define angstroms using MLayer. And I found it very useful to kind of go through this practical example. This is not how you would use MLayer in practice. This is just kind of me playing around with the interface, I would stress, but it really helped me to get straight in my head all of the concepts that Blair was talking about. As he's explained, you wouldn't just capture the unit, you would need to capture the aspect and scale, and these together would help you, particularly the scale would link to the unit. So there might be multiple scales for each unit, and it's important to store these rather than just the unit. So we would store unit cell length, the scale, and the aspect ID that corresponds to the unit as we think of it. So we can put a tick next to that requirement. Can we retrieve a name and a symbol for each unit? So again, doing a different call on the MLayer API, we can see that we can pull out the name and the symbol for the unit that matches the scale that we attach to the property. So again, we can put a tick next to that one. About conversions, can we get all the possible conversions for angstroms out of it? And again, I show how you can query the API to pull out those conversions. So there's, as Blair said, there's the conversions which are kind of lossless conversions, and there's casts where they might be some query over its validity, and they're separated out, and we can use either. So we can put a tick next to that requirement too. Some additional requirements. It would be nice if whatever we used was fully set up and we didn't have to build something. Blair, in the first version of MLayer, as he says, it's under construction. So he's got the framework there and he's seeded it. It would need some work to pad it out, but the framework is there, and we've kind of shown that it's functional. And we would be able to contribute to it if required. It would also be nice if there was a non-API based source, so we didn't have to keep hitting their API, and we can download it to use offline. And again, this is on the radar for MLayer, but it's not out there yet. And it would also be nice to be able to show to specify a consistent unit system. If you know that you're interested in a particular unit system, which again, MLayer does allow that to be defined, but this might change in the future. So we've got ticks through all those requirements, but we have identified some developments that would be needed for MLayer if we were to use it in PSDI. Some short-term ones are already being looked at. There's some medium-term and long-term requirements here, which I won't go into because of time. And I can say that it does meet our requirements. It's got very rigorous unit conversion. It does require some further population, but we also need to look at the other alternatives before we make our final decision. Thank you.
Thanks very much. In the interest of time, we will move on, but as you can see that we have the operation here is showing that MLayer looks like a really good way of moving forward to satisfy what users will need. Thanks very much, Aileen. The last talk is Stuart and Samantha is both, they come from a work where we've been trying to use semantics and support all this metadata and actually look through some of the practicalities there, so the pragmatism. So I hope you can stay for the last bit of the talk. If we could switch on to Stuart. Hopefully he'll come on.
Can you hear me?
Yes.
Okay, good.
Please.
Let me get my full screen. You see that?
Let me just see whether I need to take you through to. There we go. I think.
Can you see my slides?
No, we can see you. I think you need to take control of the screen.
Well, I don't really have that choice. Okay, all right, let me do that. We should have done this ahead of time. All right, now you should be able to see my screen.
We've got your whole screen there, yes.
Yeah, it's big, I know. There we go.
Yep,
that's better.
Perfect.
Okay,
Over
thank you, Jeremy. So let me see if I can do this double speed as if I were speeding up a YouTube video. Stuart, University of North Florida, trying to channel my best Sammy Pearman-Kanza from Southampton. We're looking at it more from a pragmatic side, and what do we have already in terms of some infrastructure from a semantic standpoint, and then kind of where do we need to go? What are the gaps we need to fill relative to this? The link below on the slide is just to another presentation that Sammy gave earlier this year that goes into more of her perspective on the pragmatic nature of what we need to do relative to AI. To paint the picture, as others have already said, we need to understand anything we need to do, we know what the context is. We need experience, which then leads to inference. Easy example, wow, it's 32 out there. And of course, we as humans can in some fashion interpret that, but to have a machine try and interpret that in some kind of logical way, no matter which way is appropriate, obviously means a little bit more. One of my favorite quotes to my students is, here's a difficult example to understand from a semantic standpoint, can, which was used to train Watson when it was the thing at that time. Of course, what we're talking about here really, though, is scientific data. And scientific data, as others have said, is hard. And it's hard to understand and represent. It's a bit more abstract because it's not typically presented in more natural language. It's described, in fact, with a different language. We've used different ways of speaking about it with some very technical words. And as others have shown, data is presented in tables and or via equations. So we need to think about how are we going to build an infrastructure that can represent the semantics of scientific data in a way that can help us get towards AI understanding scientific data. So I've got this, this onion diagram trying to represent that obviously there are many levels of information here that we need to think about. Can we untangle these semantics? What tools do we have that are potentially available for us to use to do this? Once we've done our maybe more in-depth analysis of these different levels and the connectivity between them, can we generalize those semantics? And thus, can we represent the full context of scientific experiments, which is not necessarily just how the researcher would talk about, this is what I'm studying and here's the relevant information around that. It's more than that. It's the why, and to an extension, it's the philosophy of how you're approaching it. Of course, in the end, we want to hopefully have something that is representative of the knowledge, the logic, and therefore can also be translated into AI tools that we have now, and obviously those that are developed in the future. Data is complicated. I didn't say that in too many words. We've already talked about the different pieces of what data can be represented by, but there are different types of data: raw data, derived data, correlated data, two columns of data that there is a correlation implied between those columns, but which is not explicitly stated. There are some things out there to talk about, as others have said, the semantic representation of the SI, and there are unit ontologies out there. So at least we've got those things covered, but there's pieces here that are still missing. When we bring this together into a more table format and we think about what I would call data series, where we measure physical properties over ranges of concentration, of temperature, or other variables, then we have additional information that may be presented with this, which can be very informative, but only, of course, if it can be properly interpreted. And this is something that I tried to work on in some research I've done on a project called SciData, which was to try and find a way to represent scientific data, not only in a relatively well-formed semantic way, but also with appropriate contextual metadata. But we need to think from the data further up to, well, what is it that the researcher is really focusing on? And of course, IADOPT as an RDA output is an obvious thing to bring in here because it tries to represent semantically a generic way that we can represent a variable with a particular property that's been measured on a particular object of interest and potentially having a matrix. And so this gives us a bit more context to the actual data that we're gathering, but that's still actually, in most cases, not enough. And so we still need to go further with trying to represent the context of the measurement that's been made. In addition to collecting data, we do analysis on data, and we also come up with some metrics as to whether we like the quality of the data or the applicability of the data to the particular research topic. So we need to think at this level also for how can we decide what is good quality data or appropriate data for a particular research study, and which data is really not correctly regarded for a particular question that's being asked. Then we need to think even further up about the actual approach that researchers take in terms of doing research. How can we represent how scientific experiments are put together? Why are there decisions about particular variables that you might control, but other variables you might leave off to the side and not worry about so much? The ontologies that are listed in this slide are, I have to say, more practical than philosophical, in the sense that we're not necessarily at this moment representing kind of the philosophical approach to how you're doing the research. It's more of the practical implementation of it. But we definitely need that in order to be able to understand why we do certain experiments when we don't do others. So key takeaway points here are there's a lot of stuff we have developed, mostly in isolation from a semantic representation of scientific data and the scientific process, but there's still a lot we have to do. There's a need for integration and standardization. As I mentioned in one of the first slides, we need to think about how can we generalize how we represent this information so that when we start applying it across disciplinary boundaries, that we can do that in a way that doesn't necessarily dilute what the information and the knowledge is in those other disciplines. There are definitely challenges here. We have to come up with ways to think about how to represent this kind of information so that we can go cross-discipline and even interdisciplinary, which of course are very important additional areas for advancement in science. If you have any questions, certainly, as Jeremy said at the beginning, throw them at us now or put them in the document so that we can answer them later. Thank you.
Thank you, Stuart, for getting us almost back on time. So hopefully this whole session has shown there's an enormous amount we have to do to enable communication. Lots of pieces are there, and we are trying to put them together. But what I think we've just seen there, that yes, there's lots of semantic information, ontologies are out there, but there are some key pieces missing that mean that we can't at the moment tie them together. But with the units in particular, there's a lot of progress being made, but a lot of things we have to try and see, is this going to work? Will this get out to the communities we don't normally get to? But we've got at least an attempt to start. So please, I'm not going to keep you from lunch, but please throw questions in to that document and we'll try and sort of build up a community here, because it's really important that in the various projects that are running, several that come together here under IUPAC, under CODATA, under the PSDI, but various other organizations, NFDI in Germany, and equivalent running in a number of different countries. We are trying to make it such that it is relatively easy for the researchers to record properly what they do in a way that can be communicated to the different user communities that it need to reach to, bearing in mind that some of those communities will be ones that the producer didn't even ever consider would be needing their data, and that presents real difficulties here. Thank you very much. Just join me in thanking all the speakers today, and please write notes in.